everyone for joining us for this version of the AMS seminar. A couple of announcements, at least one announcement. Well, two maybe. So firstly, we are filming this. So this will go up on YouTube at some point.
So I should keep quiet.
And the second announcement is that our very own Maxim Bichut just won a grant jointly with Ben Hobbs. So maybe a round of applause for Maxim. And finally, it's my pleasure to introduce Alper, Atamturk, who is a professor of Industrial Engineering and Operations Research at University of California, Berkeley. Alper is a very highly regarded authority in discrete optimization, particularly integer programming, both linear and nonlinear, and he has enormous experience in applications of this technology in energy, electricity markets, and more recently perhaps finance. Maybe he'll talk to us a little bit about this in this talk. Amongst his many achievements, he is a fellow of the Department of Defense. And he serves on the editorial board of all the major journals in our area, like Operations Research, Discrete Optimization, and so forth. So without any, they have something, right?
I think it's called Bush Fellow now. They changed the name.
So without further ado, he's going to talk to us about. Oh, you changed the title from what you got.
No,
you said you'd talk about submodular optimization, but maybe. Well, anyhow, he'll talk to us about combinatorial optimization with probabilistic objectives. Over to you.
thank you very much, Howard. It's a great pleasure to be here. It's actually my first time here. That was Hopkins and Baltimore as well. Good for you. The weather and the taste. Nice, delicious seafood. So this is great. Thank you. So about the title, so I apologize. I didn't realize that I changed the title. The title is, so let me start with apologies. It's more general than it deserves. I said this is essentially so two talks, and I put them together. I could not come up with a title that, that sort of merged the two topics sort of. But that's what it is. But I'll be more specific, so it's not as general as it sounds, but I'll be more specific in the next slide as to what I mean. So this is joint work with my former student, Andres Gomez. The first part is with him. He recently joined University of Pittsburgh as an assistant professor in the Industrial Engineering Department, and with my postdoc, Hemin Gion, who got her PhD from University of Wisconsin, Madison. So that's the second part. All right, so here's the agenda. So the first part is going to be on maximizing a particular submodular utility function. I'm going to define it in a second. I'll give a few motivating applications to convince you why it is interesting to study that model, and give an approximation of it. This is a hard problem. It's a pretty hard computation problem. The second part is on minimizing parametric var, and you'll see it is the same function, but it's a minimization, so the other side. In particular, I'm going to look at the case where the decisions are binary, and we'll sort of try to extend the results to mixed integer case where there are a lot more applications. All right, so let's start with the first part. So here's the model that I have in mind. So G is a univariate function from non-negatives to non-negative reals. It's monotone concave. typically, we have in mind a utility function. Could be square root, log utility, negative exponential, sort of increasing concave function, but results work for just monotone concave functions. And we have two vectors, A and C, that are negative. And we want to maximize this objective where the first term is linear, A transpose X, plus G of C transpose X. Think of this as a sort of an expectation, and this is sort of a risk term. And you'll see there are actually many other applications that fall into this framework. Now, the feasible set, we require that X be a vertex of some polytope, an arbitrary polytope. So it's a discrete optimization problem because we want the answer to be a vertex. And it is NP hard, even for very simple polytopes, such as the cardinality. Some of the x's have to be at most k. Even such simple polytopes, it is NP hard. So let's look at sort of two special cases. Not sort of special case, but variants. If I don't have this nonlinear term, g here, just maximize that linear function over the vertices of a polytope, it is a linear optimization problem, can be solved in polynomial time. That's easy. Whereas this variant, you have the same objective, but instead of constraint being x, a vertex of a polytope, if you relax it and say x can be any point in the polytope, again, that becomes a convex optimization problem. We're maximizing a concave objective over a polytope. That's also easy to solve. But when you put these two things together, that you insist that you have that nonlinear function and that x be a vertex of the polytope, that problem becomes almost hard. Is it clear what we're going to be studying? Good. Now, I have a few slides to motivate why this model is interesting. The first one is project evaluation and review technique. This is a standard model in industrial engineering sort of curriculum. We have, it's in the textbooks. You're a senior student, you know this material. So let me quickly go over it. What is PERT? So you're given a project, and the project is composed of a number of tasks that need to be executed. And so each of these tasks requires some time to compute. Think of some sort of construction project from civil engineering. And there's a precedence relationship between these tasks. So certain tasks have to be done first before you can do the others. So you can represent it with a graph, with a directed graph. And you can ask interesting questions. What is the duration of the overall project? Which activities are critical to pay attention and that lead to the duration of the overall project? And they need to be monitored carefully, and maybe they can speed up only those activities to speed up the overall project. And where should we allocate those resources to speed up? So you can ask a number of different questions here. So here's the model. We're given a directed graph, G, and here nodes denote the time epochs. So S is the start time, T is the completion of the projects, and the arcs represent the activities. So the numbers that I have on the arcs are assuming this normal random variable duration. The first component is the mean, the second component is the variance. Right? So the PERT approach that are in our textbooks, it says the following, do the following. Ignore randomness. Find the maximum length path from S to T using only the means. Okay? And that is your critical path. And then analyze that path and see, given its randomness, how long it would take, or what is the value at risk, and so forth. but it is only for that path that is that's the sort of mean, it has the mean duration, maximizing the mean duration. And we've completely ignored the stochasticity coming up with that. But that is the textbook approach. Currently, that's what we're teaching to our students, unfortunately. And you see that if you do that approach, follow that approach, it won't necessarily give you a good solution, right? The path at the top here, that has the longest duration in terms of means. The path at the path below, it has slightly less mean duration, but it has potentially much higher sort of variability, and quite a bit of time that's going to be the one that is deriving the duration of the project. So we shouldn't be ignoring it. So what we're suggesting is to, rather than maximizing the mean length path, maximize the value at risk. Maximize the path with the, or find the path with the largest value at risk. So use the variance information as well. So this picture, I think, is just from Wikipedia, showing what the value at risk is simply the quantile of distribution. You can find the value at risk for a particular confidence interval, confidence alpha, by just so it is simply the mean plus the inverse of the standard normal. So this is our standard normal distribution times the standard deviation. Now, if you want to solve the value at risk problem, here's this formulation. So xa is a decision variable. For each arc A, we have a binary decision variable. It's going to be 1 if activity A belongs to the path, 0 otherwise. And our objective is then the sort of mean plus some constant that comes from the confidence interval from the inverse CDF times the standard deviation of the duration for the chosen path. And down below, the constraints are simply balance constraints. So you're sending one flow from S to T, and all intermediate vertices, you have to carry the flow forward. So X is, since variables are 0, 1, X is the vertex of the path polytope. Okay, so this is an NP problem. So if you didn't have that component, right, over non-negative objectives, you could solve it easily, but non-negative, this non-linearity makes it difficult to solve. So that's one application. So that's what we propose instead of the standard approach. Here's another application. Assortment optimization problem. So this problem, any retailer solves some version of this problem. Think of this sort of a Google, when you do a Google search, on the right-hand side, you see ads that are appearing, right? And Google used some algorithm to place the ads in some rank there on the right side. So that is an assortment optimization problem. Think of N as the set of ads, potential ads to display, and M is the sort of advertising spots. And so we get a profit, Aij, from displaying ad I in spot J. And beta is a sort of fixed profit per click. The clicks, we get some profit. And our job is to find an assortment that is sort of this sort of placement of the subset of the ads to these sort of spots to maximize the profit. And the constraint in that case is going to be an assignment polytope with inequalities, not equalities. So if we use a multinomial logit discrete choice model, which is very common in this context, so you have this probability Pij of user clicking a ad in spot J with this probability if the assortment chosen is the subset S. Okay, that's a standard model. and that the overall model looks like this. So you're maximizing your profit, and subject to constraints. These are assignment constraints, at most 1 ad per spot and at most 1 spot per pad. And we want xij to be 0, 1 valued. And obviously, so this is the assignment polytopes vertices, that's what we're interested in. And the objective, it fits into exactly the form that we want. If you, so you can see that, so this is a x divided by 1 over x, that's a concave object. So here's another application. There are many other applications where you can use this model. Reliability of parallel systems, robust conic quadratic optimization. It's a problem that is sort of dear to my heart, so we've been working on these type of problems for some time. Multi-arm bandits, competitive physical location problems. So it is, whenever you're dealing with randomness, you're using a utility function where you have a mean plus this utility term with a concave objective is very, very common. Okay, so quick review of what's been done in this area. So that is the problem we're trying to solve. If your polytope is binary, like the examples I have given to you, although our approach is more general than that. Suppose you have a binary polytope, so the vertices are binary vectors. Then this objective happens to be a submodular object. So it's a particular submodular maximization problem. Okay. And there are many ways to approach this problem. In the literature, there are a host of approximation algorithms. So in general, submodular maximization is difficult. Submodular minimization is easy. The classical ones, it's Nemhauser and Fisher. Nemhauser is my thesis advisor. They have this sort of greedy algorithms that they've shown that the approximation ratio is either 0.63 or 0.5, depending on what kind of constraints you assume. If you have a cardinality constraint, that's the simplest set constraint that you can think of. Some of the variables is at most k.
Just to clarify, you're given the convex hull of the vertices, so you're not looking at binary points in a relaxation. What I mean is the polytope that you give me, you are really looking for vertices of that polytope, not the convex hull of the integer points in it. No? Okay. So when you talk about cardinality constraints, you're not imposing integrality on it.
This one is with integrality.
Oh,
okay. It's with integrality.
I see. Okay.
Since you have a concave objective, convex relaxation may be in the interior of the polytope, right? But we want to find a solution that is an extreme point.
Right, but but of course, I mean, I could give you a polytope and say I'm actually interested in the vertices of the convex hull of the integer points in there. You're not doing this, right? You're actually giving me the polytope and you want the vertices of that polytope.
Yes. There are more recent approaches and sort of more complicated algorithms, n to the 8, n to the log 8, and with slightly more complicated or slightly more complicated polytopes, down monotone, up monotone, and so forth. And the algorithms start becoming quite difficult, even though you make quite restrictive assumptions on the constraint set. Right? So here, the approach is assume a general submodular function, but restrict the feasible set and devise a approximation algorithm for it. What we do is different. We are assuming a specific objective, but general polytopes. We're not making any assumption on general. So we can use it for the assignment polytope, path polytope, for instance. All right. Next is the algorithm. The algorithm is extremely simple. Here's what we do. This picture is going to tell everything. So ignore the fact that you're looking for a vertex solution. So solve the relaxation problem. That's what we typically do. Solve the relaxation problem, that's easy to solve. Okay, fine. Maybe it is this point here inside the polytope. Okay. But we're looking for extreme point solution, right? So what we're going to do, we're going to take that solution, x0, and add this constraint here to the problem. Right? So the inner objective C transpose X is going to be equal to C transpose X0. So we fix that. You fix that, the nonlinear component. Well, if you fix the nonlinear component, you fix the other component as well. But now this becomes a linear optimization problem. And we solve this linear optimization problem. And this optimization problem is guaranteed to have a solution that exists, a solution that is on the edge of the polytope. Because you're introducing one constraint here, you take it out, the dimension can go up by 1. So you know that there exists a solution to this problem, and a vertex solution, take it out, can only be on an edge. Okay? So what we have seen is that there always exists a solution to this problem on an edge of a polytope in higher dimensions. It's obvious in 2 dimensions, but in higher dimensions, that's always the case. Right? Not high dimensional at most 2, at most 1, sorry. Okay. So then all we have to do, I think I'm running out of battery here. Sorry. We'll just round it, right? We have a solution on an edge. We're going to look at the 2 extreme points, and on that edge of the edge, and then we'll pick the best one. That is the algorithm. Extremely simple. Okay. And it turns out this is a very good algorithm, and has a good ratio. The approximation ratio for the square root function is 0.8, which is much better than that is known for an arbitrary submodular function over these very complicated, or very simple constraint sets. Right? And in practice, it works really very well. So definitely a big improvement in the ratio, and it works for any polytope. Okay. For more general functions, so if G is only known to be monotone but not square root, then the approximation ratio is 0.5. That's the same as the greedy algorithm, but that only works for matroid, and this one applies to again any. So depending, our analysis in the paper, so we were considering different objective functions, different utility functions for different values. But the analysis is really very simple. It's this one paragraph, because it all boils down to analyzing a one-dimensional function and finding the first value. Okay, so let's look at some application of the computations with it. The Purge application. So we have here a network we're looking at network size of 200 to 1,000. It's pretty large networks for the kind of application. We're comparing the deterministic approach, the classical approach, versus the value at risk approach that we proposed. Okay? And the errors that are reported here, finding the value at risk of the project, overall project, it is difficult. So we don't know, because we don't know its distribution. It's a complicated problem. So we simulate it. Okay? We do Monte Carlo simulations to find for that simulation what the value at risk of the project is, and compare it with the one that we are producing it. And you see that the error is improved sort of significantly compared to the deterministic version. And this takes, all of this takes less than a second to solve. It's very fast. The assortment application. For this particular application, the complexity is n cubed, log 1 over epsilon. We're displaying here is sort of times. These are milliseconds. So you see we have a 1,000 by 1,000 assortment problem, which is huge. Amazon would probably use it, but it really takes just very little time.
And epsilon is the error in your convex optimization?
Yes. Yes. And down below, the second row shows the gap, optimality gap. And that is, as the size increases, that approaches to essentially 0. So the algorithm in practice works very well. Constant submodular ratio is guaranteed is maybe high, maybe 0.8, but actually works in practice very, very well. Okay, so this was the first part. Good, we're on time. The second part, questions on the first part? This is the maximization of this utility function over discrete set. Now the second part is going to be on the minimization problem, and you'll see that it has a different flavor. Yes?
So you said it's a very simple algorithm. Apparently everything is very simple to prove as well. So why wasn't this sort of figured out before? Like, what is so insightful about this that this just works so well?
That's very interesting, isn't it? Okay, I can, without offending anybody. So the work that has been done in this area, so the submodular maximization, has traditionally been take an arbitrary submodular function, okay, and try to work with it. Okay. And but then it's difficult to work. Then you restrict the constraints, and that path seems to be a difficult path. But if you exploit the structure of the objective, in practice, you almost never have an arbitrary submodular function. In practice, you have a particular problem, you have a particular objective in mind, right? In my experience is working with practitioners that constraint changes, right? Sometimes you have that person has additional different site constraints, this and that. Constraints are more sort of changeable, but typically you have some mean risk optimization problem, objective, the data changes, but the model is fixed, right? That has not been the sort of the direction that people have looked at so far, right? In computer science literature, assume general submodular and try to deal with it. But if you fix the function, then you can exploit the structure and get much better results.
I mean, I think you're being a little too modest also. I mean, the algorithm, it is simple, but just coming up with the insight that this is what we should fix, let's fix this hyperplane, and things should work out. I mean, who tells you to do this, right?
And then proving it just like that.
So I guess I had a question about how realistic the Purge problem itself is. People actually use this methodology, and it seems a little bit simplistic, I guess. You know, like when things go wrong in projects, there's complex dependencies that typically are appearing. Is that?
I agree, and but it is used. I mean, it is taught in civil engineering. It is taught in industrial engineering. So it is the sort of classical, typical sort of task management sort of tool, and it has its deficiencies definitely. I mean, we didn't look at correlations, for instance, the interactions between, and the next part is going to consider the correlations as well. But I certainly agree with it. It is quite simple. Right. I mean, there are other models, sort of this crashing type of models, where you can speed up projects, speed up activities, and then you need to decide, where to allocate resources, you do scenario approaches. So, yeah, there are sort of more sort of complicated models, but that is what I present as the basic model. All right. Thank you. So the second part, minimization. Now, minimization of the same function. So I'm going to start with the binary case, and then move on to the mixed integer case. And the binary case, you will see that is a submodular minimization function problem. So this is the same value at risk objective. You have your mean times plus some constant times the standard deviation. Since our variables are binary, there's no difference between x and x squared here. So I can either write it with x squared, that's how you're used to seeing variance. Right? But since my variables are binary, I'm using x. It's a stronger model. It strengthens the relaxations. And f is submodular, and if you don't have any constraints, this problem can be solved by the greedy algorithm. Max Shan, who's a professor at our department, in his PhD thesis gave a greedy algorithm to solve this problem. It's very easy to solve. Now, what I want to illustrate to you is what happens if you try to solve this problem if you give it to a solver. Right? We have optimization solvers, standard packages such as Cplex, Robi, Mosaic, and you can input this type of problem, a discrete optimization problem. The objective is a second-order cone objective. They will accept it, and they will produce results. So let's, just as a sort of motivation, just see what happens if you try to solve this optimization problem. This table is a bit outdated. Cplex is the solver that we use and has newer sort of versions. It has improved a little bit, but not by much. N is the number of binary variables, and epsilon here is your sort of confidence, or 1 minus the confidence, and gaps denote the gap between the convex relaxation and the integer solution. Okay, so the higher the gap is poorer the relaxation. Okay. And the algorithm that is used is branch and bound, where you solve the convex relaxation. If it is not integer, you branch, and then you create 2 subproblems, and you solve convex relaxations again. If they are not integer, you branch. So this will be the branch algorithm, but you use the bound information coming from the convex relaxations to prune the tree, so in practice it works much better than complete enumeration because of the bounds that is used to prune the tree. Nevertheless, this best industrial algorithm software, it chokes for these problems. This is a tiny problem with 100 variables only. Nowadays, if you give Cplex a problem of this size without this nonlinear term in the objective, it would give you an optimal solution in a fraction of a second. Even though these are theoretically, they're NP-hard optimization problems, there's been so much work that is done over the decades on these kind of problems, and then you will get your answers very, very fast without that nonlinear component. But put that nonlinearity in there, all of a sudden, it starts choking. So we had to stop some of these after 30 minutes. You see that hundreds of thousands of nodes and branches being done.
When you say without the nonlinear, you get optimal, you mean a gap of 0?
Yes.
It really does give you, okay.
Yes. Yeah, provable optimal solutions that you can get very, very fast in the linear integer case. I have only one constraint here, this knapsack constraint. Hi.